Welcome! In this video, we'll be solving the problem number 168, Excel sheet column title. This is a classic and interesting problem where we'll explore how to convert a given column number to its corresponding Excel column title. Let's dive in and break it down step by step. In this problem, we are tasked with converting a given integer, called column number, into its corresponding column title as seen in an Excel sheet. For example, the number 1 maps to the letter A, 2 maps to B, 3 maps to C, and so on, all the way up to 26, which corresponds to Z. After Z, the sequence continues with two-letter combinations, such as 27 mapping to AA, 28 to AB, and so forth. Essentially, this problem involves interpreting the number as if it were in a base 26 system, where the digits are represented by uppercase English letters, A to Z. This concept provides the foundation for solving the problem. Now, let's look at the input and output formats. The input to the problem is an integer, column number, which will always fall within the range of 1 to 20 million, inclusive. The type of this input is an integer. The output, on the other hand, is a string that represents the corresponding Excel column title. This output is always a string made up of uppercase English letters. To help clarify, let's explore some specific examples that illustrate how this conversion works. In the first example, the input is column number equals 1. The output in this case is the string A. This is because the column number 1 directly maps to the first letter of the alphabet, which is A. In the second example, the input is column number equals 28. Here, the output is AB. To understand why, we can break down the number 28. Dividing 28 by 26 gives a quotient of 1 and a remainder of 2. The remainder, 2, corresponds to the letter B, while the quotient, 1, corresponds to the letter A. When we combine these letters in reverse order, we get AB. Finally, let's examine the third example, where column number equals 701. The output here is ZY. Breaking down 701, dividing it by 26 results in a quotient of 26 and a remainder of 25. The remainder, 25, corresponds to the letter Y, and the quotient, 26, corresponds to the letter Z. Combining these letters, we get ZY. To ensure clarity, let's also remember the constraints. The input will always be a positive integer within the range of 1 to 20 million, and the resulting output will only contain uppercase English letters. With these examples and constraints in mind, you now have a clear understanding of how the problem is defined and what is required to solve it. To solve the problem of converting a column number to its corresponding Excel column title, we first consider a brute force approach. The intuition here is to treat it like converting a number into a base 26 numeral system. In this system, each digit corresponds to a letter from A to Z. To find the rightmost character of the column title, we repeatedly divide the column number by 26 and use the remainder to determine the appropriate letter. For example, a remainder of 0 maps to Z, a remainder of 1 maps to A, and so on. Importantly, because Excel column indexing starts at 1 instead of 0, we subtract 1 from the column number before each division. This adjustment ensures that the mapping aligns correctly with the alphabet. The process continues until the column number reduces to 0, at which point all characters in the column title have been determined. In essence, this approach mimics how base conversions work, but with an added step to handle the one-based indexing of Excel columns. The steps to implement this approach are straightforward. First, we initialize an empty string to store the result. Then, while the column number is greater than 0, we subtract 1 to adjust for one-based indexing. Next, we compute the remainder when the column number is divided by 26. This remainder is mapped to a character using the formula CHR, 65 plus remainder, where 65 is the ASCII value for A. We append this character to our result string. After processing the remainder, we update the column number by performing integer division by 26. This reduces the column number for the next iteration. Once the loop ends, the result string contains the column title, but in reverse order. To correct this, we reverse the string and return it. The time complexity of this approach is O log 26, column number, as the column number is divided by 26 in each iteration, and the space complexity is also O log 26, column number, due to the result string. The optimized approach we use is essentially the same as the brute force method, but it emphasizes clarity and precision in handling the one-based indexing of Excel columns. This approach is efficient and avoids any unnecessary complications, making it the clear choice for this problem. A key observation here is that Excel columns behave like a base 26 numeral system, but instead of digits, we use letters from A to Z. The aha moment is recognizing that subtracting 1 from the column number aligns it correctly with the alphabet, ensuring that it corresponds to 1, Z to 26, and AA to 27. This insight simplifies the mapping process and eliminates potential errors. Among other alternatives, this approach stands out for its directness, as it aligns perfectly with the problem's structure. It is efficient, with minimal computational overhead, and simple to implement, making it easy to understand and scale for large column numbers. When comparing the brute force and optimized approaches, we notice that they are effectively the same because the task inherently requires base 26 conversion. However, the iterative implementation is preferred for its simplicity and clarity. While recursion is an alternative, it introduces additional space overhead due to stack frames and can make the solution harder to follow. The iterative approach avoids these issues, making it more practical. This method also handles edge cases seamlessly. For instance, it correctly maps single-character columns like 1 to A and handles transitions such as 26 to Z and 27 to AA. Furthermore, it scales well for very large column numbers, ensuring correctness regardless of the input size. Overall, the optimized iterative approach is the most suitable solution. It captures the essence of the problem, efficiently computes the column title, and maintains clarity, providing an elegant and reliable solution. In this problem, our goal is to convert a given column number into its corresponding Excel column title. Excel columns are labeled alphabetically, starting with A4 column 1, B4 column 2, and continuing until Z4 column 26. After Z, the sequence continues with AA4 column 27, AB4 column 28, and so on. This pattern is similar to how numbers operate in a base 26 system, but with a slight twist. Instead of using the digits 0 to 25, we use the letters A to Z, and the indexing starts from 1 instead of 0. This unique mapping forms the crux of the problem, and our task is to derive the appropriate column title for any positive integer input. To solve this problem, we need to break it down into manageable steps. First, we need to understand the mapping between numbers and column titles. Each column title is represented as a sequence of uppercase letters, and the numbering follows a base 26-like system. For example, the number 1 corresponds to A, 2 to B, and so forth until 26, which maps to Z. After that, the numbering rolls over similar to other base systems, with 27 mapping to AA and 28 to AB. To implement this, we start with the given column number, which we'll call N. We use an empty string, result, to store the column title as we calculate it. No additional structures are needed since we can build the result string directly. The key operations involve repeatedly performing division and remainder calculations. First, we subtract 1 from N to adjust for the difference between 1-based indexing and 0-based calculations. Then, we compute the remainder when N is divided by 26, which tells us the current letter. Using this remainder, we map it to the corresponding character by adding it to the ASCII value of A. This character is then added to the front of our result string. Finally, we update N by performing an integer division by 26, which effectively moves us to the next digit in our base 26 system. Once the value of N becomes 0, the computations are complete, and the loop terminates. At this point, the result string contains the entire column title, which we can then return as the final answer. There are a few key insights that can help solidify our understanding of the algorithm. First, this problem revolves around a base 26 numeral system, but with a twist. The digits are represented by letters, and the numbering starts at 1 instead of 0. To handle this, we subtract 1 from the column number at each step to align it with 0-based calculations. Another important detail is that the column title is constructed in reverse order, starting from the least significant digit. For edge cases, such as when the column number is exactly divisible by 26, the subtraction ensures the calculation proceeds correctly. For example, the remainder for 26 maps directly to Z without any issues. Throughout the process, we only use a string to store the result and a few temporary variables for calculations, making the solution efficient in terms of both time and space. When analyzing the algorithm, the time complexity is determined by the number of iterations in the loop. Since the loop runs once for each digit in the base 26 representation of the column number, the time complexity is O log underscore 26 n. In simpler terms, the number of iterations grows logarithmically with the input size, but the base of the logarithm is 26 instead of 10. For space complexity, the algorithm is very efficient, as it operates in O(1) space. The only memory used is for the result string and a few temporary variables. To better understand the process, let's walk through an example where the input is n equals 28. We start by subtracting 1, giving us n equals 27. The remainder of 27 divided by 26 is 1, which maps to the letter B. Adding B to our result string gives us B. Next, we update n by performing integer division by 26, giving us n equals 1. Repeating the process, we subtract 1 from n, resulting in 0. The remainder of 0 divided by 26 is 0, which maps to the letter A. Adding it to the front of our result string gives us AB. Since n is now 0, the loop ends, and the final output is AB. Now, let's look at a slightly larger example with n equals 701. We begin by subtracting 1, giving us n equals 700. The remainder of 700 divided by 26 is 24, which maps to the letter Y. Adding Y to our result string gives us Y. Next, we update n by performing integer division by 26, resulting in n equals 26. Repeating the process, we subtract 1 from n, giving us 25. The remainder of 25 divided by 26 is 25, which maps to the letter Z. Adding Z to the front of our result string gives us ZY. At this point, n becomes 0, so the loop ends. The final output is ZY. This step-by-step method ensures that we can handle any input column number efficiently, producing the correct Excel column title every time. This implementation solves the problem of converting a column number into its corresponding Excel column title. The process involves treating the column number as a base 26 numeral system where each digit is represented by a letter from A to Z. The algorithm begins by initializing an empty list result to store the characters of the column title in reverse order. The while loop runs as long as column number is greater than 0. Inside the loop, the column number is decremented by 1 to align it with 0-based indexing, which simplifies the mapping of numbers to the letters AZ. The remainder of the column number divided by 26 determines the current letter. This value is mapped to the corresponding ASCII character using CHR, remainder plus ORD, and the resulting letter is appended to result. The column number is then integer divided by 26 to process the next digit of the base 26 system. This continues until all digits are processed. Finally, the result list, which contains the letters in reverse order, is reversed and joined into a string using .join, result, ::-1. This produces the correct column title. The algorithm handles edge cases such as small inputs, e.g., 1, and large inputs, e.g., 714ZY, efficiently. The time complexity is O log 26 n, since the loop reduces the column number by a factor of 26 in each iteration, making the solution both elegant and efficient. This is the Java implementation for LeetCode problem number 168, Excel sheet column title. The logic mirrors the provided Python solution, using a while loop to handle the conversion from column number to title. Key differences include the use of Java's string builder for efficient string manipulation and type declarations for variables. The code appends characters to the string builder and reverses the result before returning the final string. In this problem, we need to convert a positive integer, which represents an Excel column number, into the corresponding column title. Think of this as translating a number to a base 26 system using letters instead of digits, where A corresponds to 1, B to 2, and so on up to Z, which corresponds to 26. After Z, the sequence continues with A, AB, and so forth, just like how numbers increment in a multi-digit system. For the first example, we start with column number equal to 1. We initialize an empty list called result to store the letters as we compute them. Since column number is greater than 0, we enter the while loop. Here, we adjust column number to 0-based indexing by subtracting 1, making it easier to work with the alphabet. This gives us column number equal to 0. Next, we calculate the remainder by taking column number modulo 26. This remainder tells us the letter to append. In this case, the remainder is 0, which maps to a because it corresponds to 0 plus the ASCII value of a. We append it to the result list. Finally, we update column number by performing integer division by 26, which reduces it to 0, preparing to exit the loop. Once column number becomes 0, we exit the loop. At this point, the result list contains the letters we computed, but in reverse order because we built it by extracting the least significant digit first. To get the final column title, we reverse the list and join the characters into a string. Here, reversing a still gives us a. So, the final output for column number equal to 1 is simply a. Now, let's look at the second example, where column number is 28. We initialize result as an empty list and start the while loop because column number is greater than 0. We first adjust column number to 0 based indexing by subtracting 1, giving us 27. Then, we calculate the remainder of 27 divided by 26, which is 1. This remainder corresponds to the letter B, so we append B to the result list. After that, we update column number by performing integer division by 26, reducing it to 1. This prepares us for the next iteration of the loop. Since column number is still greater than 0, we continue the loop. Again, we adjust column number to 0 based indexing by subtracting 1, which changes it from 1 to 0. Next, we calculate the remainder, which is 0 modulo 26. This remainder maps to the letter A, so we append it to the result list. Now the result list contains B, A. After appending, we update column number by dividing it by 26, reducing it to 0. At this point, column number is 0, so we exit the loop. To get the final column title, we reverse the result list and join the characters into a single string. Reversing B, A gives a B, and joining them results in the string AB. Therefore, the output for column number equal to 28 is AB. For the third example, we start with column number equal to 701. Again, we initialize result as an empty list and enter the while loop since column number is greater than 0. First, we adjust column number to 0 based indexing by subtracting 1, which gives us 700. Then, we calculate the remainder of 700 divided by 26, which is 24. This remainder corresponds to the letter Y, so we append Y to the result list. After that, we update column number by performing integer division by 26, reducing it to 26. Because column number is still greater than 0, we continue the loop. This time, we adjust column number to 0 based indexing again, subtracting 1 to get 25. We calculate the remainder of 25 modulo 26, which is 25. This remainder maps to the letter Z, so we append Z to the result list. After appending, we update column number by dividing it by 26, reducing it to 0. With column number now equal to 0, we exit the loop. At this stage, the result list contains the letters Y, Z, but in reverse order. To form the correct column title, we reverse the list and join the characters. Reversing Y, Z gives Z, Y, and joining them produces the string ZY. This means the final output for column number equal to 701 is ZY. To summarize the key takeaways, this algorithm uses 0 based indexing to simplify calculations, extracts the rightmost digit in base 26 during each iteration, and maps it to its corresponding letter. The result is built in reverse order and then reversed again at the end to produce the correct Excel column title. This approach ensures the solution is both efficient and easy to understand. The time complexity of the convert-to-title function is logarithmic, specifically log_26, column number. To understand why, let's break it down step by step. Inside the while loop, the column number is repeatedly reduced by dividing it by 26. This reduction means the number of iterations is directly tied to the number of base 26 digits in the input number. For example, in base 10, the number of digits in a number is approximately log_10 of that number. Similarly, in base 26, the number of digits corresponds to log_26 of the number. Within each iteration of the loop, there are only a few operations: subtracting 1, calculating the remainder, performing integer division, and appending a character to a list. Each of these operations takes constant time, 1. Multiplying the number of iterations, log_26, column number, by the constant time per iteration gives us the overall time complexity of log_26, column number. Using the change of base formula, this can also be expressed as log_10, column number, divided by log_10, 26. This highlights how the time complexity grows logarithmically with the size of the input. The space complexity of the function is also log_26, column number. This is because the result list stores the characters of the column title, and the number of characters corresponds to the number of digits in the base 26 representation of column number. Like with time complexity, this number of digits is proportional to log_26, column number. Apart from the result list, the function uses only a few variables, such as column number and remainder, which require constant space, 1. Even when we convert the list to a string using .join, result, ::-1, the memory used is proportional to the size of the result list and does not change the asymptotic complexity. Therefore, the overall space complexity remains log_26, column number, as the storage required scales with the number of base 26 digits in the input. When comparing approaches, a naive method might involve iterating through all numbers up to the given column number to map them to their corresponding column titles. This would result in linear time complexity, n, which becomes inefficient for large inputs. In contrast, the optimized solution leverages the mathematical properties of base 26 arithmetic to compute the column title directly. By reducing the input size logarithmically at each step, the time complexity is minimized to log_26, column number, which is the theoretical lower bound for this problem based on the number of base 26 digits. For best case analysis, when column number is small, such as 1, the loop runs only once, giving a time complexity of 1. For both average and worst cases, larger values of column number result in the loop running proportional to the number of base 26 digits, leading to a complexity of log_26, column number. This demonstrates that the solution is efficient across all scenarios. To mathematically prove the time complexity, let's define d as the number of digits in the base 26 representation of column number. The relationship between column number and d can be expressed as 26 raised to the power of d1 being less than or equal to column number, and column number being less than 26 raised to the power of d. Taking the base 10 logarithm of this inequality gives us d1 log_10, 26 equals log_10, column number, d log_10, 26. Simplifying further, we find that d is approximately equal to log_10, column number, divided by log_10, 26, plus 1. Asymptotically, d is proportional to log_26, column number. Since the number of iterations in the loop corresponds to d, the time complexity of the function is log_26, column number. This proof confirms that the logarithmic complexity aligns with the function's behavior, providing an efficient solution for the problem. When solving this problem, there are a few common mistakes to watch out for. First, off-by-one errors in indexing are a frequent issue. Remember, Excel columns are one-indexed, meaning column A corresponds to 1 instead of 0. This can be tricky because many programming problems use zero-based indexing, so you need to explicitly adjust your calculations by adding or subtracting 1 where necessary. Another mistake involves incorrect character conversion. For example, a common error is using CHR, remainder plus 65, instead of CHR, remainder plus ORD, 1. This happens because people forget that the letters A through Z map to numbers 1 through 26 in Excel's column system. Always ensure you're correctly mapping remainder values, so 1 corresponds to A, 2 to B, and so on. Finally, failing to handle carry properly can lead to infinite loops or incorrect results. Once you process a digit, the column number should be reduced using integer division by 26. Without this step, the algorithm can get stuck or produce the wrong output, so make sure you're consistently updating the column number in each iteration. Now, another issue to be mindful of is infinite loops in edge cases. For instance, if your column number is very small, such as 1, incorrect loop termination conditions can result in your program running indefinitely. To avoid this, you need a clear stopping condition, such as while column underscore number 0. Additionally, you might encounter problems with overflow when handling large numbers. While Python's int type can handle very large integers, this might not be true for other languages, which could lead to unexpected behavior. To prevent this, choose languages or data types that support large numbers, particularly if you expect inputs at the upper limit of constraints. These fixes not only ensure correctness but also make your solution more robust for edge cases. Understanding the underlying pattern in this problem is crucial. At its core, this is a base 26 conversion with an offset. Familiarity with modular arithmetic will help you map indices correctly. Interviewers often take this a step further by asking follow-ups, like reversing the process to convert a column title into its corresponding number. They might also challenge you to adapt your solution to handle arbitrary bases, so understanding the general principles of base conversions is essential. When writing your solution, prioritize clean, readable code over premature optimizations. A clear implementation is particularly valuable in interviews, where clarity often matters more than squeezing out minor performance gains. Finally, testing is key. Make sure to check edge cases like column numbers 1, 26, and 52, as these involve transitions where carry handling is critical. This thorough testing approach helps ensure your solution is both correct and reliable. There are a few alternative approaches to solving this problem, each with its own trade-offs. One option is a recursive approach, where you repeatedly reduce the column number and append the corresponding character at each step. While this can result in elegant and concise code, it may lead to stack overflow for very large inputs due to deep recursion. The iterative approach is often preferred because it avoids recursion limits and is easier to debug. Using a while loop, you can process the column number iteratively, which makes the solution more robust. Additionally, in languages like Java, a string builder can be used to construct the result efficiently. This is particularly useful when dealing with large strings, as it optimizes performance by avoiding repeated string concatenations. However, keep in mind that this adds some language-specific complexity. Overall, the choice of approach depends on balancing elegance, performance, and the constraints of the specific problem you're tackling. Great job! To wrap up, we solved the Excel sheet column title problem using an approach based on modular arithmetic. This is a great example of how understanding number systems can help in problem solving. Thanks for watching, and don't forget to like and subscribe for more content. Keep practicing and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!